Okay, good morning, everyone. Please sign your attendance first. Okay, is my voice is audible for to you? Is it clear? Hello. Can you hear me well, student?
Yes, sir.
Okay. So last day we go through the how to compute the limits on trigonometric functions. I hope you studied well. Then today one of the very useful applications in limits. Today we are going to talk within the session. So I don't know whether we have to complete all the parts, but let's start and let's continue the session. Today I am start from the continuity, right? So using the limits, we can find out whether the function is has a continuity in between at the point or in between a 2 point. That means a range, right? Okay, so I will put a title for today's first part of the session. It's called continuity. Right? So let's try to understand this one first. Let's say a function of a curve, right? Let's say curve. A curve is continuous. If it has what? No any hole or breaks we can call break or any asymptote. Right? You know what are those? Right? We can say when we have a curve or function is if we need to find or tell this one is continuous, then it should have no any hole or break or asymptote during the region. whatever we are talking or we are considering, right? That's the thing, right? So let's say our function that's noted down from the f. If f is continuous, right? F is continuous. Let's say at the point C, if so we can call f is continuous at a point C. That means first we are considering a point. Later, let's move to the range. First, try to understand how we define a function continuous at any given point called C. So we can say this function is continuous at C if and only, right, through these three states. First one is FC, right, is defined. That means we have a value, this function called f now. So at that function, at the given value of the point C, it should have a y value. That means the function is defined. That's the idea. So if it has a value, this fc is defined, because we can plug in the fc value to the function, then we can find that y value, right? Let's say x is c, so y is fc. Just plug in the value to the function, then we can find the y value for that particular c point. So if we can find out this fc value, that means this point is defined. That's the first one. Second one, limit of fx when x approach to c, right, must exist. What is that meaning? The function of fx function, the limit of this fx function when x approach to c must exist. That means there should be a limit, right? First one is the fc is defined. Second one is limit of fx must exist. If this is not exist, that means at that point there is no continuity, right? If this fc also not defined, then we can say that function is not continuous at that point, right? But let's say this one is true and this one is true, then we have to consider the third one, right? Limit of fx when x approach to c should be equal to fc. If this one is true, then second one is true, then these two should be equal. Then and only we can say this f is continuous at the point C. That is the mechanism we have to follow. If we have a check-in option, we have to check these three. Then if these are okay, that means we can say f is continuous at point C. So that means if you see directly this limit of fx when x approach c is equal to fc, that means definitely this f is continuous. No need to verify these two, because this third part is okay means these two already okay, right? True, right? That means you only need to look at this part directly, then you can say this one is continuous. But if not, you can check whether it's defined, then you can say this is not defined and therefore this function is not continuous at the given point C. Or you can say the limit of fx is not exist when x approaches C. Therefore this function is not continuous, right, at the point C. That's like you can say the answers, right? Okay, let's understand this tree first. So I will draw a very simple curve, and there is a hole at the point. Let's define C here, right? Now tell me, right? Now I will ask what happened to first statement, what happened to second statement, and what happened to third statement. This FC, right? Is this FC defined at this point? See, tell me the answer. Can you find a value? This is the function f, right? Can you find the value FC inside this function? Yes or no?
Yes.
Recording in progress.
Then what is the value? Why? Okay. Why did you say yes? මේ C කියන point එකේදී x point එකේදී ඔයාට මේ function එකේ y value එකක් හොයාගන්න පුළුවන්ද?
Yes, sir.
Yes. Okay, then I will clear a little bit. This is the function, and there is a hole at the point C. So this one is hole, right? Hole means there is no y value at this point. That's the idea. So that is why we are calling this one as a hole, right? Because there is no defined value for function. So that means we cannot find a FC value, because it is not defined inside this function, right? Can you understand it? Because there is a hole. In here you can say, if you, let's say this is B, if B is defined, there is a value. That is not a hole. But at this point, what's happening? It's a hole. So there is no value for give the particular C. Right? That means FC is not defined. So the answer is no, FC is not defined. Right? So first statement is right. Did you get the point? Hello. So the given answer, I don't know the person name. So please understand this. In any point of this side or this side, no matter, there is a defined value. So that means at that point, this function is well defined. But the point where we consider it, right? At that point, FC is not defined. There is a hole that, according to my graph, you can see it, right? So first statement is not true, right? That means false, right? So we don't need to find out others. That means this one is not continuous at the point C, but let's take others. The limit of fx. Now tell me the limit of fx when x approach to C. Is this exist or not? Is this exist? Please tell me. When you consider the limit of fx when x approach to C, you can consider from the right hand and you can consider from the left hand, and these two values are equal. That means this limit of fx when x approach c is exist. So now my question is, in this curve, the limit of fx when x approach to c is exist or not? Yes or no? අපේ පළවෙනි ස්ටේට්මන්ට් එක වැරදි. okay. Then මගේ ප්‍රශ්නේ මෙන්න මේ පොයින්ට් එකේදී මේ ෆන්ක්ෂන් එකේ ලිමිට් එකක් පවතිනවද? මම දැන් කන්ඩිෂන් කියව ලිමිට් එකක් පවතිනවා. අපි normally කරන්නේ අපි right hand එක check කරනවා, left hand එක check කරනවා. ඒ දෙන සමාන නම් අනිවාර්යෙන් එතන ලිමිට් එකක් තියෙනවා. අපිට ලිමිට් එකක් find හොයන්න පුළුවන්. මගේ ප්‍රශ්නේ තමයි දැන් මේ curve එක දිහා බලලා ඔයාලට කියන්න පුළුවන්ද මෙතන පොයින්ට් එකේ ලිමිට් එකක් තියෙනවද නැද්ද? පවතිනවද නැද්ද? ලිමිට් එක පවතිනවද නැද්ද කියලා යහන්න.
Yes.
Yes, sir.
Yes. Limit. There is a limit. There should be a limit according to this curve. There is no jumping or break position. That means if this curve is like this, then there is no limit, because when you come from the left hand, it converges into this point, and when you come from the right hand, there is another value for that limit. So that these two are not equal, right? But in here, there is a limit, right? So second part is okay. Yes, it is exist, and we can write the limit as a fc, right? But no need to write down it. Right? Let's mark this. Yes, this is exist. Right. Third one, limit of fx, right, should be equal to fc. Now we know that fc is not defined, so this one also fail, right? This statement is fail. So we can say this is not continuous at the point c. Right? So by looking this curve, we can check, right? That means there is no function defined well, but we have a graph. Using this graph, we can see there is a hole at this point. Therefore, fc is not defined, but limit is there, right? But you can see this due to this fc is not defined, we can say this function is not continuous at point c, right? Let's check another one. Now the second one I have already drawn. We have a function, but there is a break. This is the function, right? So this is the point c. Now check this statement 1, 2, and 3. Is there any value for fc? That means fc is defined or not at that point c?
Not defined.
Any other answers? See the curve correctly. Right. Is there any value for fc?
Yes.
Yes. Yes. Why? See, at the c, you can find the value. Right? Using this portion of this curve, right? Here it is the highlighted point. That means c is defined, right? There is a value for c. So first one is correct. That means true, right? Then check second one. Limit of fx when x approach to c. Now tell me, is that true or false?
False.
Yes, when you consider left hand, it has a one value. When you consider right hand, it has another value. These two are not equal. That means limit does not exist. So second one is fail. That means false. Right? So third one is already wrong. So we can say this one also not continuous at point C, right? When you have a graph like this, and you can define whether this function is continuous or not using this technique, right? Right. Please give me 1 minute. Okay, thank you. Then let's take another example. This is the point C, right? So now you know the shape of these curves. What is this, right? Okay, this is the point C. Let's consider two options, two states. Let's check this one first. Okay. Now tell me whether the FC is defined or not. First statement is true or false according to this curve.
False.
Yes, false. Then second one, whether the limit is exists or not when x approach to C.
No.
No or yes.
Yes,
Exists.
plus infinity.
Yes, there's a limit, but it is positive infinity, right? So second one is true. Okay. Then we know that first one is false means definitely there is no this one is not continuous at point C, but that means the statement is also false, right? Then I will change this curve a little bit. I'll put a value here, right? Now tell me, now the FC is defined?
Yes.
Yes, because there is a value at the C. You can find out it using the graph, right? Earlier it is not, but now it has, right? Now, whether the limit is exist?
Yes.
Yes, right. Now we have to check the third option, third statement.
Yes.
Whether this FC value is equal to limit of fx when x approach to C. Is this condition is true or false? True or false?
False.
False. Why? Limit of fx when x approaches to value is positive infinity. This one fc, you can it is lies in here, right? Not the infinity, right? So these two are not equal. Therefore, right, that statement is not true. That means this one also, again, we can say this function, right? According when considering this function, you can say this is not continuous at the point C. You can write down, right? Okay, now I think you have some idea, right? So this one I explained graphically, right? To take the understand about the this check, right? This test of the continuity. Okay. Now let's take some real example. Right. My problem is are these continuous at x equal 2, let's say 2 is the problem, right? So I will define the function fx is x squared minus 4 divided by x minus 2. Right? Okay. Can you tell me by applying the test of the continuity, can you tell me whether this function is continuous at the point x equal to? What is the first one? Is this defined at x equal 2? That means, can you find a value for f2? What is the answer?
It's all.
Yes, it is a whole, right? Mean of that at point 2, there is a whole. Then, is this f2 is defined or not?
No.
Not defined.
Not defined, right? So, first statement is there. Anyway, let's check the second one. Can you find the limit of fx when x approaches 2?
Yes.
Yes, can you tell me the value?
4.
Sorry,
4.
x minus 2, then x plus 2 is remaining. When we apply 2, that means 4. Yes, value is 4. Right, this one is correct. And third one, obviously, false, right? Okay. Then can draw this one, how this function is behave actually. That means this one is equal to x plus 2, right? At the point 2, there's no value. This is the whole. So at the point 2, this function is not continuous, right? Okay, first your testing is now over. Now second one is a second example. Let's take a function called gx. Okay, it's square, the same function I will take x squared minus 4 divided by x minus 2 when this is not equal to 2, we can use this one, right? And at the point x equal to, this gx function is defined as like when x equal to, this value is equal to 3. Now tell me whether the f2 is defined at x equal to, according to when considering this function gx. Sorry, this one should be g. G2 is defined or not?
Defined.
Yes, defined, because we have value. When you consider this function, at x equal to function value is 3. Yes, this is defined and G2 equal to 3. Okay. Second one. Limit of gx when x approach to 2. While when you check this one, you can find whether the limit is exist or not at when x approach to 2. This one is true or false?
False.
Why?
Uh,
Can you
to
find the limit at when x approach to 2? Can't you find the limits when x approach to 2? When x approach to 2. Tell me. You can, yes, you can find the limits because we are not considering the exact point x equal to, right? To find the limits, that means we come from the right hand and left hand and check whether the limit is exist or not, right? When whether in here limit is actually equal to 4, right? So second statement is true. Now we have to check the third one. Is these two are equal? What is G2 value? We have to check whether G2 and limit of gx when x approach to 2. Okay, what is the G2 value? It is equal to 3, right? What is limit of gx when x approach to 2? It is equal to 4. Is these two are equal?
no.
No. Then this statement is false. So that means again this gx function, right, it is not continuous at the point x equal to. So when you draw the function again, in very similar to the first one, but there is a value for x equal to, that is here. This is 3. Right? The function, when you draw the function, it's look like, right, at the x equal to, there is a value. When x approach to 2, there is a limit, but these two are not equal. That's the idea, right? So this one is not continuous at the point 2, x equal to. Okay, let's check another one. Let's check. Let's take the function called hx. Now we have the same relation x squared minus 4 minus 2 when x not equal to 2, and we have a value for hx when x equal to 2, right? Now we define the new function called hx. It's look like this. Right? Okay, now tell me first one, whether the function is defined at x equal to, yes or no?
Yes.
Yes. What is the value for f2?
4.
4. Right. Now tell me the limit of, this is not h, f, this should be h. Now tell me the limit of hx when x approach to 2. Is this exist? If
Yes.
this is exist, okay. Yes. If this is exist, what is the value? What is the value?
4.
4.
Oh, yes, 4. Now you can check the third option. Now tell me, if these two values are equal or not?
Equal.
Equal. Okay, third one is true. Then that means this hx function is continuous at the point, right? Point 2. Right? You can write down because this function is actually pass your test, continuous test, right? Then you can say, yes, this is continuous at the given point x equal to. Right? I think now we have an idea. Okay, this test is only for only single value. Right? This test is only for a given single value. Okay, now you have to test a function within the given range. Right? Within the given range. That means you have to check the continuity of a function within the given range. Let's write down the first. If f is continuous at every point between a and b, is the range. Number is a and b. Then we can write f is continuous on this interval, right? If f is continuous at every point between a and b, right? When you consider the full domain, right? We choose a special region in between a and b, right? Then if we can say this f is continuous at every point between a and b, let's say a and b like this in the number line, you can say, if you can say the each and every point, right? When you consider each and every point in between a and b, if f is continuous, then you can write down this, then f is continuous on this interval, right? Okay, but we consider the bracket. If you see the bracket, right, this is not a square bracket. There is the idea. That means the direct value endpoint of the interval a and b not included to this range. When you write down like this, because this is not a square bracket. If you write down the range as like this, that means a and b also included to this range. If you write down it here, the meaning of that, at the point a also and the point b also, the function is continuous. So we have to define something more, right? Because using the earlier test, you can find whether the function is continuous or not at any point, but you cannot use that test for the endpoint. Why?
It's a continuous.
Why you can't test? Because it is defined. First one is okay. You can find out the value. You can check whether there is a value for fa or fb, right? But second one, can you do it? Limit of fx when x approach to a, can you find? Or limit of fx when x approach to b, can you find out the value? Why? Can you can't? Because normally limit is defined, you have to come from the right end and the left end. This point also, this should be valid. You have to check from the right end and the left end. But when you consider the point A, there is no, you cannot consider the left end. You can only see the right end because this range is within the A and B. Right? This function is, you are talking or you are considering function within this range. So this is out of range. So you cannot check this limit of fx when x approach to A from the negative end, you cannot find. As well as here, you cannot find the limit of fx when x approach to B from the positive end, right end. Because function is, we don't know function is defined or not, because we don't have the values for that. Right? Okay. So we have to define a new rule to check the endpoint. Right? In between, we can find any point, right? Because we have a test. But at the endpoint, we have to define a new rules. Okay. What is that? When you test the endpoint, you have to follow this. In general, right? Continues from the left at point C, right? We can write limit of fx when x approach to C we are calling continuous from the left at point C. That means this one. Sorry, from the negative end. This one should be equal to FC. Right? Let's draw the graph first. Now I will draw again. Let's say considering 2 point. This is A and this is B. Let's assume that. Then you can see there is no defined function for the below than A. When x is below less than A, we don't know how the behavior of the function. So we are at the endpoint. So when we check the continuity check at the endpoint, right? So this one is defined C. Could be any point, right? Any endpoint, that means A or B, right? So in here, C negative means you have to come from the negative, that is, this one is defined this point, right? Okay. So limit of fx when x approach to C negative means you are come from this function to this end, and if the limit of that one-sided, this called one-sided limit, no? This one-sided limit of this point is equal to fc, that means it's equal to this point, the defined value, then and only we can say this point also should be included to the range, right? As well as you can write limit of fx when x approach to C from the positive end. Positive end means you are coming from this end, right? if this one is equal to C, right, then and only this endpoint also should be included in fully range, right? If not, we cannot put this bracket, square bracket. So we have to stay from this normal bracket, right? So when we draw this graph again, I will do something for this graph and try to understand this. Here, the value is well defined, and I will put a hole at the endpoint. Okay? So now tell me, how about the point A? Is that should it be? Is this need to include for this range or not? And tell me how about the point B? So this is given the idea about the point B. This is given the idea about the point A. Let's first consider the point A. So limit of fx when x approach to C. Now here C means A, right? That means limit of fx. I write down this for general, in general, right? For our case, x approach to A from the positive end. This one should be equal to A if this point is continuing or continuous within this range. Or that means now we are considering the endpoint only, right? So because we can check other points no matter using the previous test, but here we are going to define a new rule to check the endpoint. A rule is this rules. We have to check two endpoints using these rules, right? We have to only consider the one-sided limit of the function, and we have to check the defined value for at that point, and we have to check whether these two are equal, right? So what happened to fa? Is this defined? There is a hole.
Not defined.
Defined. Then this point A should not be equal to this range, right? So we have to put this bracket. How about this point?
B is defined.
Yes, let's check it. Fx when x approach to B from the negative end, and test fb also here and test these two are equal. That means we are checking first and second and third, these three statements as like the previous case, because first check this one, second check this one, and thirdly check whether these two are equal. When you check the third one directly, that means first one and second one already test inside that. Okay, fb, yes, it is defined. Then limit of fx when x approach b from the negative end. Yes, it is exist, and the values for this one and the values for fb, these two are also equal, right? Then we can include the point b to the range. For this, when we consider this function, right, we have to write the answer as like we have to include the b point, but we can't include the point A. So we have to write down like this. This function is continuous within this range, but range is like this. Right? So now you have an idea. If f is continuous at every point between A and B, right, then f is continuous on A and B. Right? First, we check the inner side of the range. Right? This is the first test. After that, we are going to check left hand or corner of the functions. This one need to check. This one need to check. Then, using the answers coming from these three, we can write the range of the continuity. So that's the idea. Okay, let's do an example. This is the example. Right? Prove fx equal square root of 16 minus x square. So this is the function. This is the problem. Is continuous on this range. Now this is the problem. We have to prove. Right? Is continuous on this range. So when you consider the range, this endpoint also included, right? Because this has a scalar. Okay, now check. First thing is we have to prove this function is continuous within the range. That is this one. Then we have to consider this point, that means lower end, and we have to consider the upper end. In both, then 3 are equal or true means yes, this function is continuous on this range. We can write down this. That's the idea. Let's do this one first. Okay. I'll write down the order. First, check this range. Right. In general, we can write down this limit of fx when x approach to c. That means limit of 16 minus x squared when x approach to c. We have to check this one within the range whether this function is continuous, right? Then we have to check limit of fx when x approach to, let's check first look this one, positive 4, right? I will check the endpoint first. That means we have to check limit of 16 minus x squared when x approach to positive 4. What happened? We have to check and prove. Third one, we have to check limit of fx when x approach to 4. Negative 4 when x approach to negative 4 from the negative end. Right? Okay, we have to check the limit of fx when x approach to negative 4. Is this correct? What I am writing here? We have to we are right when x approach to 4 from the positive end. Give me 1 second, I have a call, right? Okay. Is there any mistake? Yes, we have to check the limit of fx when x approach to 4 from the negative way. Yes, I have write down many. We have to check this one first. Then we have to check limit of fx when x approach to negative 4 from the positive way. That means limit of 16 minus x squared when x approach to negative 4 from the positive. This one also need to change. It should be negative. Sorry, negative end, positive 4, negative end. This one negative 4 from the positive end. Now it is okay, right? Okay, let's now elaborate this test. I'll write first one here, right? Limit of fx limit of fx when x approach to c. I will write down a general term when x approach to c. That means this one. So limit of fx means square root of 16 minus x squared when x approach to c, right? Okay, now I will hand over to you this one. What is the limit of square root of, what's the limit of a square root of 16 minus x squared when x approach to c? Can you write down the value as like this? Just plug in the value of c onto the function. Because that one, when you find the limits, first thing is you have to just plug in and see what happened. That's the first part. If there is a problem, then you have to do something more. Even you can't solve the problem, that means limit does not exist, right? I first plug in the value, the c. C is in a general term, right? C may be within the range from negative 4 to positive 4, right? Anyway, can you tell me, is that true for all this range? First, let's say c is equal 5. Let's take 5. Right. If c is 5, what happened to the inside of square root? 5 square is 25. Now this one is negative. So this one, right? So we cannot say, we cannot plug in the value equals 5. But here, definitely we know that our range is within negative 4 and positive 4. Right? Can we plug in the negative 4? Yes. 16 minus 16. That is equal to 0. Can you plug in the positive 4? Yes. 16 minus 16. That is equal to 0. But we have value. Right? 0 means value. There is no any problem. We can plug in the value. And the other values, what happened? Minus, let's assume the sum numbers in between range. Minus 3, minus 2, minus 1, 0, 1, 2, 3. Any other decimal point, 3.1, 3.2, you can substitute. That means this one valid for any number within this range. This general term, no? C might be a number in between minus 4 and plus 4. So, but anyhow, we can write generally this one. There is no harm to write this equation, because we know that C is in between negative 4 and positive 4. Right? If C is equal to 5, we cannot write. But definitely we know that C is in between negative 4 and positive 4. So there is no harm. So we can plug in the value. Right? Therefore, that means we can write down this. Plug in the value means FC is defined. As well as limit of fx when x is equal to c. That is also this one. No? That means limit of fx when x is equal to c is equal to fc. Right? That means at any point, c means any point. Right? When we consider any point in between this range, this continuous test is true. Right? So first part is over. We prove this function is continuous in between negative 4 and positive 4. Okay. Then we have to check the endpoint. How to check the endpoint? Here, I wrote it. Check limit of fx when x approach to 4 from the negative end. See what happened. Then check limit of fx when x approach to 4, negative 4 from the positive end. You have to check, right? I will write down the answers for it here. Okay, let's check this one first. Limit of fx when x approach to 4 from the negative end, right? We can just plug in the value. First check when x equal 4 means 16 minus 16 again equal to 0. We have a value. In here, what happened? Limit of fx when x approach to negative 4 from the positive end means just plug in the value and see. 16 minus again 16. Square of negative 4 means again 16. Negative 4 times negative 4, that is equal to 16. Right. This one, 16 minus 16 means again 0. Right. These two are 0. This is F4. This is F minus 4 actually. Right. Okay. Now see what happened now. You have checked the limits first. Limit is equal to 0. And you can check whether this value is defined or not at that point. Okay. How to check it? Just plug in the value again. Then we know that definitely these two are equal because F4 means, right? you can put f for x equal 4 here, and it is equal to 0. Then limit of fx when x approach to 4 from the negative end is equal to f4. Right? Second statement is true. Right? Third statement. Limit of fx when x approach to negative 4 from the positive end. This one also true. It is equal to f minus 4. Yes. This one again true. Now test is over. We prove the within the range. We prove the continuity test within the range. Then we check the endpoint, two endpoint. Again, these are true. Then we can write this statement: fx is continuous on square bracket of minus 4 and plus 4. We prove that. Right? Hope you understand it. මේක පොඩි සංඛ්‍යා ආරම්භයක්. Right? අපිට ටෙක්නික් එකක් දීලා තියෙනවා. We have a technique. We have to follow that technique. කොහොමද මුලින්ම මේ ටෙක්නික් එකේ රේන්ජ් එකක continuous check up එකක් කරන්න ඕන නම් මුලින්ම කරන්නේ මොකද්ද? රේන්ජ් එකේ end point දෙක අතරලා within the range මෙයා continuous කියලා proof කරන්න ඕන. අපි general term එකක් අරගෙන අපි proof කරනවා a general term එක through yes what limit of fx when x approaches c equal fc means c may be any point in between a and b. That means all over the range this one is valid if we prove this. So first we have to prove this, then that the answer coming from this test is this one is valid for within the range a and b. Then we have to check the endpoint. Endpoint එක check කරන්න. Endpoint එක එක පැත්තකට අරලා endpoint check කරන විදිහ මම කලින් කියලා දුන්නා. Endpoint වල අපි මේ theorem එක එතකොට දාගෙන තියෙන්නේ නැත්නම් මේ test එක හදාගෙන තියෙන්නේ one sided limit check කරන විදිහට. මොකද අපිට මේ දෙපැත්තක් නැහැ endpoint වල. එක පැත්තයි තියෙන්නේ. එතකොට එක පැත්තක් තියෙනකොට one sided limit check කරනවා. ඒ limit එක ඒ point එකේ define වෙන value එකට සමානද කියලා බලන්න. එතකොට function එකක් තියෙනවා නම් අපිට value එකක් හොයන්න පුළුවන් just plug in the value. That means f4. Then we have to check the limits. One sided limit. So limits කොහොමද කරන්න කියලා ඔයගොල්ලෝ දන්නවා. limit එක මේ විදිහට ලියාගත්තට පස්සේ මේක solve කරලා answer එක කීයද කියලා කියන්න හොයන්න ඔයගොල්ලෝ කලින් ඉගෙනගෙන තියෙනවා. ඒත් මේක තමයි limits. ඒත් මේ application එක තමයි continuity test එක. ඒත් limits වල application එකක් තමයි continuity test. So this checking the continuity means one kind of application of the limits. So first at the beginning of the class you have learned how to find out the limits of any given functions, right? Then now we apply this knowledge into an application, that means continuity test, right? අපිට එතකොට මේක one sided limits බලන්න පුළුවන්. එතකොට one sided limits okay නම් ඒ values උත් එක්කවල ඒ define වෙන value එකට සමාන වෙනවා නම් right අපිට end point දෙකත් මේ range එකට දාන්න පුළුවන්. ඒකට අපිට මේ කියන මොනවා හරි statement එකක් true ද false ද කියලා අපිට proof කරන්න පුළුවන්. So we can prove the statement, any given statement given in the question, right? Okay. Right, next part again you have to use these properties. Actually these are properties, right? So you have to keep mind and use, because we cannot prove the properties, right? We just use the properties. So properties right. assume that f and g, there are two functions, f and g are continuous at point C. C කියන point එක තුල f සහ g කියන ශ්‍රිත continuous කියලා assume කළොත් මෙන්න මේ properties අපිට use කරන්න පුළුවන් මොනවා හරි continuous check එකක් කරන වෙලාවට. So we can use these properties to check whether the functions are continuous or not within the range. So what are those? F plus g is a first one. Then we have to think about f minus g, then f dot g, right? These are continuous at a point C. So if we consider the f and g are continuous at the point C, then the combined functions f plus g, f minus g, or f dot g, these are also continuous at point C, right? ඒ කියන්නේ අපිට මේ function දෙකක් තියෙනවා නම් අපි දන්නවා නම් ඒ දෙන්න continuous කියලා. හැබැයි function දෙකේ එකතුවක් හරි subtraction එකක් හෝ ගුණිතයක් multiplication එකක් තියෙනවා නම් පැහැදිලිවම අපිට කිසිම proof එකක් නැතුව මේ property එක පාවිච්චි කරලා කියන්න පුළුවන් මේ function එක continuous කියලා. ඒ දෙන ලද point එකේ. මේවා අතර properties, right? Just use. You have to keep it in your memory and just use, right? Fourth one, what about the f over g? This one also is continuous at point C, but we have to write down this unless gc equals 0. f over g is also continuous. f over g කියන එකත් continuous කියලා කියන්න පුළුවන් දෙන ලද point එකකදී c කියන point එකදී, but ඒ වෙලාවේදී gc කියන එක බිඳුව වුණොත් එතකොට f over g continuous වෙන්නේ නැහැ. මොකද denominator එක 0 වෙලා එතන define වෙන්නේ නැහැ මේ function එක f over g function එක. එහෙම වෙන්නේ නැතිනම් පමණක් f over g එකත් continuous කියලා මේ property එකේ කියනවා. So we have four properties, right? About the combining functions. So we can just use those, right? Right. Then let's learn something more. If a function is continuous at a point C, right? Then we can write down this limit of fx, right? When x approach to C, this should be equal to C. This is our theorem, right? So earlier, what we have done, we check this one first, and we can say this function is continuous at point C. But if someone say a function is continuous at a point C, that means we can write the inverse case also. Limit of fx when x approach to C should be equal to fc. Right? Okay. Now assume that this f, this function, is a polynomial. When the f function is a polynomial, right? then we can write down this property as like limit of, I will use the term called p to show it is a polynomial function. Px when approach to c is equal to pc. Right? No harm, no? Because this f is general function. Now, if this function is polynomial, we can write down it is in this form. Okay. Right. But we know this property because at the beginning we learned this one. What is that? Every polynomial is always continuous everywhere. Okay? Every polynomial is always continuous everywhere. We learned this at the beginning of the class, right? So now we know this one. So now I'm going to prove a new one, right? That is why I use this term. So I need another space to write down the remaining part. So I will delete part. Right, because I need to tell something about this f over g, right? I'm going to tell about the f over g case, right? So let's take now. Let's take a rational function. Right? What is a rational function? Rational function means one polynomial divided by another polynomial, right? So this one is, let's call px, and this one is qx, right? So a rational function px over qx is continuous. Right? Everywhere except what? Qx equal to 0. Because if the qx is 0 means denominator going to 0. There is a problem at that point. Okay, why did I write down this? Because here we learned some property, right? Inside this property, the last property is f over g is continuous at point C unless g is equal 0. Now we choose a special case, right? Because these two are function f and g, right? These are now we are going to relate this f and g onto p and x, right? So p is a polynomial if and q is a polynomial, right? Now we have a division of these two functions. Okay, so if this one is polynomial and denominator also a polynomial, we call this as a rational function, right? Now we are talking about that means rational function, right? So if these are rational functions, we can say it's continuous everywhere, right? Except qx equal to 0, right? What happened to if this rational function have a discontinuity, then we can write down this. If you have a discontinuity means right? You have discontinuity means sometimes you have a hole because qx and px, both of them are maybe going to 0 at that point, then sometimes you may have a hole, or you may have a asymptote. Means constant divide by 0 situation. When you just plug in the value and you have a constant divide by 0 situation, that is asymptote. So these two situations may happen when you check a rational function. When you check the continuity of the rational functions, sometimes you may comes up with these problems. Sometimes at some point it may have a hole, or it may have asymptote. That means the function, the rational function, it is discontinuity. At this point, you can write down this. So that's the idea, right? Okay, I hope you got the point. These are some additional advanced things inside the finding of continuity, right? I can stop at the beginning some point, but I will teach you all the things inside up to some level, right? If you need more, there are more, okay? If you need more, you can serve lots of reference and you can go through the deep of the calculus, but I will touch some up to some level of the calculus, right? Okay. Now let's take example and try to understand. Example. Let's take fx equal x squared minus 4 divided by x squared plus x minus 6. Right. My problem is find the discontinuity. That means this, if there are any or low asymptotes, my problem is find out that. That means definitely this function, this, what is this function? Here this one is polynomial, this one is polynomial. Polynomial divided by polynomial means this is a rational function. So this is a rational function. Inside the rational function, sometimes we may come up with the discontinuities, because sometimes it may have a hole or sometimes it may have asymptotes. So sometimes both these are available inside this rational function within the range of the considering range. So now my problem is find out the discontinuity. That means definitely this one is not continuous, right? So I am asking the points that may given the discontinuity. So what we have to do? Right? Try this one. Okay. Let's check the answers. When x equal 3, and the answer when x equal 2. Test. Right. So, any discontinuities may happen due to the denominator part. That means qx equals 0. Right? Then we have a discontinuity. That means, according to this part, qx equal to 0 means what is the qx here? X squared plus x minus 6 equal to 0. Then you can find out the factors. X minus 3, x plus 2, right? That means x minus 3 equals 0, or x plus 2 equals 0, and x equal 3. Sorry, I think this should be changed. This one is x plus, this one is minus, right? X plus 3, minus 3. Then x equal minus 3, and x equal 2. Right, these are the points. Minus 3 and the plus 2. Let's understand what happened to the equation when we apply the negative 3 here. Upper part is not going to 0. It has a value. That's a value. I'm asking that. I'm referring you the point called at x equal to 3. This one is constant value. This one is constant value. And the denominator going to 0. So this one is asymptote. Right? At x equal to 3. Then what happened to at x equal to upper part going to 0, lower part going to 0, then this one should be 4. So these two are the discontinuity points. First one x equal negative 3, it is called as asymptote, and when x equal to this, we can define as 4 because of this one, 0 divided by 0. Okay, now you know this one in a rational function, if it has a discontinuity, how to find out the points, discontinuity point. Okay. Right, I will give another problem. This problem is fx equal modulus of fx, right? Continuous everywhere. This is the problem. fx සමානයි මාපාංක x කියන එක continuous check කරන්න நம்ம point එකම මේක තමයි එතකොට fx define කරන විදිය. This is the way of defining fx. So I will give some help to you. This is a modulus x, no? That means we can write down it as like this. fx modulus x can be defined as like this when it behaves as x when x is greater than 0. This one can define negative x when x is less than 0. So we can definitely write when x equals 0, modulus should be 0. So I will give some hint. The task is you have to prove this, right? Using the there's some, you can use the terms that we are learned at the previous section, previous means not the earlier one, right? Very recent one, and you can write down this one is continuous. So this is the definition of the modulus x, right? When you write down this, now it is very easy. So I will draw a curve for this. This is the graph of modulus x. So tell me what is this and what is this? Just called x. So this one is negative x. But we can write down those as a what? These are polynomial. Right? These two are polynomial. So now we know that every polynomial is continuous everywhere. So inside this fx, we divide into three sections because these are the modulus x now. So we know that when x is you have to change this, okay? No, right. Here, this is minus x. Fx equal negative, right? So this one should be what? Continuous. Because this is polynomial. That should be continuous. Again, this is fx equal x. This part also continuous function because of this one also polynomial. Now this one is continuous, this one is continuous. Only thing is we have to think about this point. Okay, let's do it. Limit of x when x approach to positive 0. First I will write limit of fx. Then you have to think about what is fx when x approach to positive 0. 0 in positive way, not the positive 0, 0 in the positive way. What you can choose? Limit of x, fx when x approach to positive 0 means in this sense. Then you have to choose fx as x, right? So this one, you know that going to see. Then you have to find out the limit of fx when x approach to 0 from the negative way. Right. That means limit. Here you have to choose negative x because you are look at here. Negative x when x approach to 0. Again, this one is going to 0. So these two are equal. That means limit of x when x approach to 0, limit of fx when x approach to 0 is exists and it is equal to 0, right? Okay. And you know that according to the definition of the modulus of x when the x equals 0, that value is 0. So you can write down again limit of fx when x approach to 0 is again equal to f0. So this one is for true. Now you check in this range and this range and this point. Both are continuous. That means this range, through this range, it is continuous. At that point, it is continuous. At this range, it is continuous. So you can write down this. Yes, the answer is yes. Yes, fx equal x modulus of x is continuous everywhere. You can write down like that too. Right? Okay.
Recording stopped.
Right. Today I will close the session at now, right? Because I have to go back again to the practical class, right? So sorry for the inconvenience issue because the timetable is crashed, right? So I will cover the missing time later, right? So let's meet on next Tuesday. Sorry, next Wednesday. Right. After later, I will do extra class. Okay. Thank you very much.
Thank you, sir.